Welcome to section 1.5, memory and its contents. This is a book I'm going through lectures for each section. I'm Picone. My co-author is Garbini and Devine. Helped write the book. There's a copy available for you at MIT Press, just to sell it a little. And here's the rtcbook.org companion site to help you navigate the material and the course that accompanies it. Okay, memory and its contents. Memory is not content specific. It doesn't have to represent anything specific. It can be used to represent, for example, the following: numbers, like integers, floating point numbers, signed numbers, etc. It can also be used to represent codes, like character codes and numeral codes that we're familiar with and that we will also introduce in this lecture as well. And then also instructions. The programs that we write will be stored as instructions in memory. The programmer must keep track of the meaning of the contents of memory. Example, 2 bits could represent each of the 4 directions. So we could have 1, 1 represent north, 0, 0 south, 0, 1 east, and 1, 0 west. But I just chose those pairings because they were the obvious ones that made sense. No, because it was an arbitrary choice. I could have chosen 0, 0 to be north, for instance. Okay. Given that the state of every bit of memory can be represented by 0 or 1, we can think of memory as containing numbers, even if its meaning is not necessarily a number. Okay, so north isn't a number, but it can be represented by the number 1, 1, if that's what we choose as the representation of north. Memory organization. In memory, bits are grouped into bytes of 8 bits. A byte is often presented as 2 nibbles with the contents of each represented by a hexadecimal numeral. For example, we have the byte, 8 bits. We have this space in the middle, so we see 2 nibbles of 4 bits, and we can represent them either by the binary numbers, as we do in the top row, or by the hexadecimal numbers, D4, which would be more common. Hexadecimal is used in part because it's so easy to represent bytes like this. Each byte is given a unique positive integer address distinct from its contents. Okay, for instance, consider the following portion of memory. So we have a column for the address and we have a column for the contents. So at address 2, we have contents given by this byte. There is an address for each addressable unit of memory, in this case, for each byte. Multi-byte numbers and endianness. Multiple sequential bytes can represent a single number. The byte representing the higher powers of 2 is called the most significant byte. The byte representing the lower powers of 2 is called the least significant byte. So MSB and LSB are the acronyms that we use. When storing a multi-byte number, there are 2 conventions. Big endian, which is that the most significant byte is stored at the smaller address. You can think of it as coming first in memory as you're counting up in address. And little endianness, where the most significant byte is stored at the larger address. Consider the integer here. So we've got 4 bytes, 32 bits. 2 raised to the 31 power in base 10 is represented in binary by this 4-byte number. An example of how this would be stored in memory using the big endian and little endian conventions is shown in this figure. So we have the big endian table and the little endian table. So for big endian, we would put the most significant byte. This is the most significant byte. This is the byte representing the biggest portion of this number. We put it at the lower address. So most significant byte first, then the less significant bytes thereafter. Little endian, in this convention, the address that is lower is the least significant byte. So we start with the last of these bytes, the rightmost, and we put it at the first address, and we go essentially backward from right to left in this number in memory. Okay, so big endian and little endian are both used. So you just have to know in the context which is used in your system. Number of distinct values represented by n bits. A conventional number of bits can be used to represent different types of objects in memory. For instance, in many systems, the standard integer type is represented by 32 bits. The total number of distinct values that can be stored in n bits, the formula for this is 2 to the n, for typical values of n. So 1 byte, 8 bits, there are 256 distinct bytes. 2 to the 16 for 16 bits, we get 65,536 different distinct values. In 32 bits, or 4 bytes, we can represent just over 4 billion different objects. And finally, 2 to the 64, another common number of bits to represent an integer as. We have well over, we're into the trillions and even beyond. Those are the number of distinct values we can represent with n bits. Things commonly stored in memory. Given that memory can store information with any meaning whatsoever, remember north, south, east, west, like we started with as an example. There are no bounds to the types of objects that can be stored. However, there are several common types of objects explored in the following slides. First, unsigned binary representation. Numbers could be stored as unsigned binary. Recall that unsigned binary represents non-negative integers. Here are the non-negative integers that can be stored in 1 byte, 8 bits. We have 0 through 255 for a total of 2 to the 8 or 256 different positive integers represented. We can and usually do use more than 1 byte to store non-negative integers, but this is an example with a single byte. Commonly stored. Numbers in 2's complement signed binary. This is how we represent negative numbers in computer memory. As with unsigned binary, 1 byte of memory can store 2 to the 8 or 256 integers. For signed binary, these integers are negative 128 to positive 127, instead of 0 to 255 as it was for unsigned binary. Again, as with unsigned binary, multiple bytes can store a wider range of integers. Okay, another thing commonly stored. Numbers in binary coded decimal or BCD representation. A binary coded decimal represents each decimal digit with a nibble, so a series of nibbles can represent a decimal number. This leads to slightly less dense storage because we could store more things in a nibble than each of the 10 characters. But it is still useful for high precision computation. For example, recall from the chapter that the number 421.73 had an infinitely long binary representation, and therefore to store it in memory it would require truncation. Represent this number in binary coded decimal. Let there be an implied decimal point, as some encodings define, between the 3rd and 4th nibbles. The BCD representation is as follows. 4 could be represented with this nibble, 2 with this nibble, 1 with this nibble, 7, and 3. So each of these decimal numbers are represented with a nibble in binary. Therefore, the BCD representation is given here where they're all strung together. Commonly stored, again, floating point numbers. Floating point numbers can represent very large or very small numbers with limited space. It is for computer memory what scientific notation is for a small piece of paper. It represents a number as a sign, a significand, which is also called the mantissa or coefficient x, and an exponent n in base 2, which is conventional, the sign times x times 2 to the n. Consider the following illustration of a 32-bit floating point representation. A sign bit s is followed by an 8-bit unsigned integer exponent e, which is followed by a 23-bit sequence of bits interpreted as 1 point digit 1 through 23. So sign bit, 8-bit biased exponent, and then 23-bit significand. This can be interpreted as the number -1 raised to the s, so that's the sign that turns it positive or negative. 1 point the d1 through d23 times 2 raised to the e minus 127. That's the bias in the exponent. For instance, we can represent the 32-bit floating point in memory as 0, and then we have our 8-bit biased exponent, and then we have the digits thereafter. It would be interpreted as the decimal -1 raised to the 0, so this sets the sign. -1 to the 0 is 1, -1 to the 1 is -1, so it's either +1 or -1, times, this is binary for 100, which is our exponent here that gets biased by 127, and this is our base 2 number with a radix point 1 point digits, 1 through 23. So that converts to 1.0078125 in base 10, and we can multiply it out to represent this number, which is a very small number, and it can still be represented in 32 bits. The last thing we'll consider are characters that can also be stored in memory. In addition to numbers, memory can store character codes. For instance, encoded alphabets, special symbols, and emojis. The most common character code is the ASCII code, which is a standard set by ANSI. It's a 7-bit code, so there are 128 unique character codes, shown in the table on the next slide. We'll take a glance at it here. Okay, so it's a pretty comprehensive table. The lower codes, the lower numbered codes, are control sequences that can be used by different devices to have conventional meaning. So if you send a certain character code to a device, usually that character code is interpreted the same from one device to another. For instance, the character 8, which we can look at here, 8 is backspace. Okay, so that's the description of it. The character is abbreviated BS. It has hexadecimal numeral value 08, and in decimal we would say it is just 8. So this is a control sequence code. The graphic characters of the higher codes correspond to familiar character representations, the Arabic numerals, the Latin alphabet, and common punctuation marks. If data in memory is known to be encoded in ASCII, it can be easily interpreted accordingly. So let's take a little closer look. So once you get through all of these control sequences, the higher numbers, so these 3 columns here, this column, this column, and this column, represent other characters, including here are the numerals 0 through 9, Arabic numerals. And here's our Latin alphabet. Here are the capital letters down to here. And then we have the lowercase letters across over here. So we also see some punctuation, some brackets, braces, etc. Underscore. There's a radix point, negative, plus, parentheses, $sign, etc. So this is the code, and it is very common, and we'll use it for our LCD. So more on that soon. All right, we'll see you next time.